Hi guys, and welcome back to Fabscaped. Now, while all the videos I'll be making during this course are rather important for understanding this vector drawing for digital fabrication concept, this video is probably the single most important video for understanding this concept that we teach throughout this course. This video is about thinking fab. I like to use this phrase, thinking fab, for being able to, think the way we do to actually design. How do you think to be able to design an object like we'll be doing, or these projects that we'll be doing? How do you think an object onto this paper? How do you think it onto this canvas so that I can actually fabricate it? Well, what is thinking fab? Thinking fab is the ability to see physical objects not just as the materials they are composed of or the general parts they're made out of, but as the fundamental 2D shapes or 2D geometries, you might say, that they are made out of. So it's reconstructive engineering. This is basically all it is. It's 2D, it's 2D to 3D design. We're taking things, well, you can even say 3D to 2D to 3D design because I'm taking an object. Let's say if I have an object right here, I'm taking this cube right here and thinking of it not just as, oh, this has fab on it. This is a nice cube. This is black. Um, I can really think of it as, hey, this is six sides. This is six equal sized squares. These are the real essential 2D geometries to making up this object. I can break that down. I can put it on an Inkscape or an Illustrator or something like that. I can send it to my machine, and I can reconstruct my cube. So that was 3D because I saw it there, to 2D to 3D, and it can also be just 2D to 3D where you can think of an object that you want to create, and you can just basically draw that 3D object in 2D parts and then fabricate it. So we're going from 2D to 3D. It's all about breaking an object into its most basic shapes. So let's try that right here. Let's imagine that we have this hammer right here. How can we break this into its most basic shapes? If I asked you, what is this hammer? If you weren't thinking fab, you might say, oh, this has a nice metal head. It has this nice this hickory this genuine hickory handle, and it has this nice rubber backing right here. You might say that. However, if you were thinking fab, you would say, well, let's see, what shapes do I see? What shapes do I see? What shapes do I see repeating? What shapes do I see only once? What shapes are important for for the proper function of this hammer? And once you say that, you can say, hey, look, this is a silhouette maybe. You might be able to think of this as a silhouette. And you can see this silhouette might be duplicated along, this side of the hammer because I know I have this claw part. So then I can see how you can break this down, see how you can cross section this thing in the easiest form possible to recreate this object. So let's do that. So we have this our hammer. We basically took it. We found a silhouette of this hammer, and we put this on the paper or on Inkscape, and we made our cross section where we have our two duplicates on one side, and we have this part with the claw part basically sandwiched between them. So they're stacked up like this, and we have our tabs right here that can go through these holes that are 3 times thicker than the material we would be cutting out of, so that when we cut this material out, we can basically take these tabs and we can slide them right in there, and they can hold our hammer in place. Once we have that, once we've basically done this drawing, we're basically done. We give this to the machine, and the machine says, okay, I have this picture. Let me go ahead and let's cut it out. But now, since it's cutting out this picture, you know that this picture isn't just a picture. This picture is actually an object. So then after it's done, you can take it, you can actually put it together, and we have a working hammer. We have a working object. So being able to understand this concept is huge. Being able to take something and think it apart, basically, think it into its parts, think it into its most basic geometries is super important. We'll be doing this all throughout this course. Let's say I might have a picture of a windmill or of a fan or of a chair, and we're going to say, let's think this thing apart. Let's do our thinking fab. Let's do our reconstructive engineering on this. And we'll have to take it and find all these basic parts that it's composed of, and we'll actually rebuild it in its 2D parts on paper or on Inkscape, and then we'll go ahead and we can actually send this to machine and we can cut it out and we can actually have our object that we're making. This is huge, as I said. And if there's one concept that I would stress more that you learn, it is this concept. It is this concept of this reconstructive engineering. Once you can understand this, this course will be a breeze, and you'll be able to, you'll be able to think faster than I will. All right, what are the steps to this process? How do we think fab? How do we do this this reconstructive engineering? Let's say we have this table. We have to think first. We have to think about. We have to find. We have to draw our essential 2D geometries. Well, what is an essential geometry? What do I mean by that? Well, an essential geometry is a geometry that without it, the object cannot function properly. So for an essential geometry of this table, it might be the top. The top has to be there for the table to work. A table is only a table with a top. A table is also really only a table with legs. And in this case, this table only functions properly with this support beam going through it to keep these legs in check and to sort of help give some extra support to the table top. So we're going to find these 2D essential geometries. Then what we're going to do is we're going to add relationships between these essential 2D geometries. So basically determine, so now that we know what this shape is, and we know that this is what this shape right here is, we know what this shape up here is, how do these fit together? What relationships are there between it? This doesn't just fit on top of the table, this has to fit underneath because we know what it does. So this finding and adding relationships is really the same thing as saying, okay, what do these parts do? Why are they important? And if there is a relationship that, or if a geometry that you think is essential doesn't really have any other relationships to anything else, and it's just sort of a standalone piece that really doesn't do anything for the for the well-being of this table, then it's not an essential geometry, and you can remove that out of your essential geometries list for that object. And then after you add these relationships between our essential 2D geometries, we can find and add non-essential geometries. Like, let's say if you had a clock on here, or let's say if you had words typed on here somewhere, or let's say if you had pictures engraved. Those are all non-essential. They're non-structural. They don't really add to the structure of the table. It's almost like a house. The beams are structural. The paint is non-essential. It's not. The house can be just as strong without its paint as it can, with its paint. The paint doesn't determine the strength of the house. All right, so let's do this with this table. Let's go ahead. Let's start solving these problems. So let's step one. We know that we have a top. Well, and as we make this top, you can see this top is rounded. Well, is the rounding really essential to the formation of the table? Does the table have to have a rounded corners? Well, no, it really doesn't. So that's sort of a non-essential geometry. So we're going to leave that out of our drawing right here. And by the way, when we're doing this drawing in particular, we're not really focused on, as far as precision, as far as making, objects a certain width or a certain height or stuff like that. This is just for demonstration purposes. In other videos, I'll show you how to, set exact sizes and do all that kind of stuff. We won't even add tabs to this table, let's say, like we saw with the hammer, to make sure things fit exactly perfectly together. We're not going to do that. And for this project, we're just going to sort of draw our basic shapes. Alright, so we have our top. We know we need our top. We said that the legs were also essential, so let's draw some legs. Now when you're drawing these legs, you have to think of something. These legs, what purpose do they serve? Since we know what they are, right? So let's go ahead, we can draw them. Let's duplicate my leg, and I'm going to duplicate this. I'm actually going to make this into our support beam. So our support beam is longer. Support beam, let's say it's like this. Let's pretend a support beam looks like this. So we found and drew all of our essential 2D geometries. I'm going to change its color so you can basically tell them apart, let's make these ones blue. Our legs are blue. Yay. So now we have all our essential 2D geometries. Now let's find and add our relationships between them. Well, what are some relationships we have between these essential 2D geometries? Well, we know that the legs determine the height of the table. So let's figure out how high we want our table. Does this look like a good height as far as, the width? You can see how this table is maybe about 2.5 to 3 times or 2 times ish as long as its table as it is high. So let's figure this out. Let's say, yeah, this is about good. I could say that this is maybe about good as far as the height of my table. Let's say these legs are about about half these legs make the table half the height of my table. And remember that the height of the legs really determines the height of the table, right? Because as high as the legs are, so is the table. Of course, minus the top of the table. But really, as high as the legs are, so is the table. So now we have that geometry squared away as far as that relationship. But then we have to think about this. Okay, how wide are these legs? This is sort of important. Imagine if these legs are pretty skinny. Let's say these legs are like this. And remember, we only have 2 of them in this case. Guess what? This table is going to be rocky, and we don't want it to be rocked. We don't want it to rock around. So guess what? We're going to make our legs wide enough. So let's make our legs, let's say, about this wide. We don't want them extending past the table top, where they could, make sharp corners. They can hit people. Imagine if this leg right here stuck out, it could hit people. So let's make our legs about this wide, so they give us enough support on the ground, but they don't stick too far out. We can delete this guy because now we don't even need him anymore. We'll duplicate this guy again. And now we need to basically add our relationships between our legs, our table top, and this support beam, because we know that let's figure out what this does. We know that this rear attaches to these legs. We know it attaches to the table top. Let's say to help to keep the table stable, and it provides some support right up top there. So let's figure it out. First of all, we know that the support beam doesn't extend completely into the table. We know that it actually only extends between the table legs. So we need to rotate it so that we can understand how far our legs will come, because we know that this support beam is right between them. And if the support beam is too long, which means that it's going to basically push the legs out too far. And imagine if the support beam was as long as the table is long, or longer, then guess what would happen? The legs wouldn't even really be able to be underneath the table. So let's say that our support beam is about this long. Let's say we want the distance between our legs to be about this and this, right? So now we have our support beam. We have the relationships between our support beam and the tabletop. Now let's figure out our relationships between our support beam and the legs. Well, in this drawing at least, this rendering of a table, the support beam basically extends halfway down the leg. Now this is sort of semi-important. I mean, for practical purposes, if you have a support beam that extends too far down, you can't really put anything under the table. If it doesn't extend far enough down, guess what? Our legs become wobbly. These things can sort of rotate in. There's going to be a lot more stress up in the higher parts of the table, right underneath the top, because the beam won't be wide enough and long enough to provide adequate support. So let's say it's about halfway. So this is actually pretty good. We can maybe change it a little bit, but now this is good. Now guess what? We have done the first 2 steps. We drew our essential geometries, then we went ahead and we added our relationships between our essential geometries, and now we are all set to add our non-essential geometries. Now since we've done this, since we have our exact or our estimated essential 2D geometry, outlines and sizes and stuff like that, we can basically add all kinds of things, all kinds of cool things. So one thing we know about this table, this is really the only other geometry that's there in this table that's non-essential, is the rounded corners. We know our top is rounded, so we can round these corners. Let's say we rounded them to about there. This looks pretty much like our table. So now guess what? We have really just taken this table and we have reconstructed the entire thing. We have our top, it's rounded. We have our legs, and we have our support beam. Now, just to be safe, because since we're doing our support beam structure, and we know that this tabletop is rounded, we know that the support beam extends these legs. Let's just make sure that these legs, since this is rounded, guess what this does? This sort of makes the table a little smaller in these regions. So what we're going to do is we're going to make sure that our table, that our support beam doesn't cause our legs to extend too far. And this is the only place where, let's say the rounding of the corners would actually play into any sort of structural role in our making a table. But now since we know how the table is made, we can have a better understanding for why let's say if we change the way the table looks, we can understand why we're doing it. So let's figure this out. Let's say that this was in the center. I'm actually going to go ahead and put this in the center of this object. Let's align this to the center. Now let's align. Let's bring this right here up. And guess what? We're fine. Well, what I'm doing right now is I'm basically checking to see if this right here came past, because it came past the rounded corner, because you can see how it makes the table a little bit narrower at that end, and that might have made our corner stick out past the edge. But guess what? We're fine. There's nothing to see here. This is all good. We're ready to go. Now imagine if I had actually put tabs on this. So imagine if I had put some tabs here, or I could even just go ahead and print this right here on my laser cutter, on my big router. I could actually make a table right now, and I could put screws or something like that in it. And guess what? I would have a table that worked. And I would know it works because I have my 2D geometries. I know what they do, and I know why they do what they do. So this whole process is extremely important in Fab and in our critical thinking and in the thinking, thinking Fab and thinking in this whole reconstructive engineering process. I hope this video was useful. I hope to see you guys in the next videos. We'll talk about in the next videos we'll talk about building our complex shapes. So imagine if this table was all kinds of different shapes. We can talk about all of that. Or if we're making all of our other kinds of projects and stuff like that, how to make these complex shapes, how to edit text and stuff. We'll talk about all that kinds of stuff in the next videos. But this video is extremely important because it really teaches this reconstructive engineering aspect. And without it, it's going to be extremely hard to understand the concepts of this course and then to understand, why did he put that there? Why is he making a bunch of those? Why do I have to do this if I want to to achieve this desired effect? But if you understand this concept, it would be easy because you'll be able to tell, yes, of course I need this here because this does this, and you'll understand why we use the parts the way we do. Imagine if I wanted to add other geometries to this table. I can do that now. I can add all my drawings. I can add all my other things. I can add more legs. I can elongate my table. I can do whatever I really want to do now because I understand this. Alright, I hope this video was helpful. I hope to see you in coming videos. I really look forward to this course being a blast, and I can't wait. See you guys later.